first up this morning is Matt Horn from RPS. And Matt is the director at RPS in South Kingston, Rhode Island, where he manages a team of experts, of both engineers and technical staff. He's a senior scientist specializing in unmitigated and mitigated response of oil spills. He's got 10 years experience at RPS. He's including experience with the Deepwater Horizon oil spill. He's provided expert testimony evidence on several regulatory hearings, both here in the US and Canada. And Matt's going to really discuss how operators have really transitioned from using some of the desktop tools and onshore HCA analysis and applied them in the offshore scenario. And I thought this was a really interesting presentation because obviously we've been doing onshore HCA analysis for years, looking at streams and rivers and topology. But what happens when we translate that into an offshore environment where we have winds and currents that are changing all the time? So this has really taken this problem and really magnified it exponentially. And Matt's been doing some really interesting work on how to leverage the power of the GIS and analytics to really solve and answer this question about what happens when there's a pipeline incident offshore. So with that, I'll turn it over to Matt.
Thanks for the intro, Jeff. So I'd like to speak with you guys today about the offshore HCA analysis we're now currently doing for a number of different operators associated with pipelines in the Gulf of Mexico. What we're doing is we're using some of our in-house tools and Esri-based visualization and analysis steps to identify high consequence areas for pipelines in the offshore environment. So what I want to do today is walk you through a little bit of spill modeling 101. I'm going to show you about some of the traditional inland approaches we've done with HCAs and AOI impacts. Those are high consequence area or other areas of interest. In that traditional inland approach that many of you have likely seen in this forum as well as many others. And then I want to talk to you a little bit more about some of the new approaches we've been using in the offshore environment. Specifically, I want to look at the development and application for offshore pipelines. And I want to show you then some example results and conclusions to kind of talk you through how this is a little bit better than our previous approach. So for those that aren't aware, spill modeling has been used for planning, preparedness, assessments of consequences from releases of hazardous substance. And there's essentially three questions we look at. Their trajectory, fate, and effects. If there's going to be a release, where's it going to go in the environment? How would it behave? And ultimately, what would that mean from a biological or socioeconomic perspective? Now, for an HCA assessment, really what we're looking at is the is, what, or when questions. Is a resource affected? If a resource is affected, what is that resource? And then, when would it be affected? How quickly could that resource be affected? So this is a tool that many of you may be familiar with. This is OilMap Land. It's our overland and downstream transport model. It's a two-dimensional model that's an OilMap Land extension for GIS. It runs on the GIS platform and produces GIS outputs. And what we're looking at is how oil is going to move over the land surface, adhere to land cover, flow down slope, essentially, filling pools and depressions, evaporating, spreading, and then ultimately leading to a waterway where it can be transported with the current of the waterway at the specific velocity at each downstream reach. Oil could be retained on shores, evaporate, or spread radially in lakes. We use automated processes in GIS basically to identify HCAs that could be affected using overlay analyses. And here we're showing you some traditional outputs in the top left, looking at some trajectories of where releases could ultimately get onto the land surface in brown or make their way into waterways in gray. What the mass balance of the oil is, and what mass balance means is if you have 100 barrels that gets released, how much of that could evaporate? How much of that could stick on land? How much of that could be found on the river surface or the lakes? And then the image on the right actually takes kind of a combination of the two of those outputs and kind of mashes them together, looking at the minimum time. Essentially, if there is a release, how quickly could that oil move over the land surface and then move downstream? So here we're looking at oil, in this case, leaving a rail corridor where we've got some land pooling in these orange areas. If you see my mouse here in the middle right of the screen, releases entering waterways and then flowing downstream, and that line going from a red soon to a blue, i.e. it takes a lot longer for the oil to get down there. This works in the on-land assessments because elevation rarely changes. We run an interval-based approach where we've got a couple hundred releases that are simulated over hundreds or thousands of kilometers, and we basically get a set of outputs that kind of holds throughout the year. We use some automated tools to then process other layers of interest, these HCAs, to then identify, in this image on the right, the overall number of HCAs, so we could identify that maybe 80% of this pipeline has the potential to affect an HCA, or we can break them out by ecological resources, drinking water resources, other protected areas. I think you can kind of see where I'm going here. This is the traditional HCA or AOI for the terrestrial assessments that we've been talking about. But when we get into the Gulf of Mexico, things get quite a bit different. We've got currents to contend with. We've got tides, we've got rivers, there are winds and waves, and all of these are spatially and temporally variable. Here, what I'm doing is just looking at some of our IUCE EDS model viewer data of the NOAA RTOF's currents and NOAA GFS winds on top of one another. And if you were an oil particle sitting on the surface of the water, you could imagine that depending on where you were in the Gulf of Mexico, you're going to be feeling a lot of different pressures to move in different directions based on these driving forces of winds and currents. And a traditional HCA assessment simply cannot factor these changing dynamics in. If we were to run a release here in April and a release here in January, it's very likely that that oil could go in a different direction. And just like that oil could go in a different direction if it happened at 6 p.m. versus 6 a.m. with an ingoing or outgoing tide. So what we're doing now in the offshore environment with a couple operators is applying our SciMap or OilMap tools. SciMap is a spill impact model application package, and it's actually a four-dimensional trajectory, fate, and effects model. What we're doing is we're looking at oil moving on the surface in the water column and looking at how it can evaporate, how portions can dissolve into the water column. We're looking at a number of different fates processes. I don't want to walk you through all of these, but what we do is we discretize a release. We break it up into many thousands of different particles and then allow each one of those particles to move through the environment to figure out where oil would go. Now, that would be great if we had a single release, but when we're looking at an HCA assessment, we're trying to capture an understanding of what would happen if this release happened at any point in time. So what we need to do is apply what's called a stochastic approach. And what I mean by this is a very big word for a very simple process. On the left-hand side here, we have a number of different trajectories. What's a trajectory? Basically imagine that each one of these releases is that very bad day that happened. Maybe that orange one is April 3rd at 3 p.m. And we'll see where that release goes based on the winds and the currents. Maybe that magenta one is January 24th at 7 p.m. It goes a different direction because the winds and the currents and the tides were doing a different thing on that day. And what we can do is by staggering the start dates over multiple years, 5 to 10 years, and running hundreds of different scenarios with randomly selected start dates, we can begin to develop a statistical approach to determine where oil has a likelihood of going. It's a statistical analysis of not only determining the probability oil will wind up in a given place, but by looking at all of these results stacked up on top of one another, we can identify the minimum amount of time that it might take for oil to get to a given region. Now, we look at individual representative trajectories and environmental assessments, maybe looking at individual 95th percentile worst cases, and we can parse things out by summer or winter, but that's not necessarily necessary in this case. What I want to do here is basically use these trajectory results on the left, stack up a couple hundred runs, and then on the right-hand side, look at where these probability footprints overlay with specifically resources of interest. Now, I just want to think about three different hypothetical cases. Let's imagine that you have a pipeline, it just comes right offshore, and it runs out to a facility, maybe a gathering line, and that's this image on the left. If you had a pipeline that was oriented like that, you're likely going to want to run a release at the furthest offshore point. And a release, I mean 100 releases. And what that is going to do is say, look, if releases from this most offshore point can reach land or breach an HCA, then it's very, very likely that the rest of your pipeline could. And we don't need to run releases every 100 meters back to land because you already know the furthest offshore could touch a resource. So that entire pipeline would be a could effect. In another case, let's just imagine that you had a pipeline that spanned a gap and it went from land to land, but there was water in the middle. In those cases, you might want to run a release at the furthest offshore location. In this case, it would be the center of the pipeline. right? Because if that specific point could affect receptors, then it's very, very likely that the rest of the pipeline could. In another case, you might need to actually run several releases. Let's imagine if you had a pipeline that extended from this location and went up into Mississippi Sound. You know, you've got that pipeline traveling through 3 different hydrodynamic environments, 3 different potentially ecologically sensitive environments, and you might need to run several different release cases. But what we would do is then take those results and we would overlay them on the high consequence areas in the region. I realize that this is an absolutely ridiculous simplified depiction on the left to identify high consequence areas. This data is typically considered confidential, and the operators provide this to consultants like myself so that we can do these assessments. But the key here is that we're taking this footprint in the offshore environment with all of these different environmental forcings, identifying the location and the type of resources that could be affected, quantifying the number of resources that are affected, and then determining the minimum amount of time it might take for an oil spill to impact that specific resource. When we're doing these kinds of assessments, what we typically do is a single kind of a release case, and that's the most persistent oil type that's either collected or transported in the pipeline system. We look at the worst case discharge volume as defined by PHMSA. That's the release time times the shutdown time times the flow rate. So actively pumping out until the pipeline is shut down, and then allowing the volume within the pipe to release, which is the entire volume in the pipe. These volumes are very highly conservative. They are much larger than any volume you would anticipate to come out of these pipelines, but this is a conservative approach and would give you the safest way of saying, look, if these are the total number of resources that could be affected. To maximize the amount of oil hitting the environment in the shortest amount of time, we basically make the spill duration near instantaneous, and we run it out for 30 days. That's another highly conservative assumption, because now we're looking at oil moving throughout the environment for 30 full days, completely unmitigated, no emergency response tactics being employed. And the reason we're doing this is because we want to find out what's the maximum spatial extent oil could move should there be a release that was untouched. In this case, we looked at 7 years of spatially and temporally variable data. We had three-dimensional, actually four-dimensional temperature, salinity, currents, and winds. And we marched that forward for a couple different example cases that I'd like to walk you through. So some of the key results we provide, if you remember back to the is, what, and when questions, is we provide that minimum time footprint. We can either show the probability oil would go in a direction, or we could show the bullseye of here's the minimum amount of time it would take for oil to move out from the release location. And what we've done for a couple of these operators is cropped that to the first HCA impacted. Right, I've got 30 days of results, but that's a little excessive because we know that's not a reasonable use case when emergency responders are typically out there in hours. So the minimum time footprint tells us a little bit about what is affected. We can then take that data, sort it with GIS, and then basically identify out of the different HCA types, what is the minimum time to the first impact, and then what are the specific, say, location exactly or state to those receptors being employed. And this image on the left kind of demonstrates how the time progresses from this magenta, about 12 hours into a release, to the purple, about 12 to 24 hours into a release, to the blues, which is getting into the 48 hours into a release. And for a release in this offshore environment, we predicted that oil would impact an ecologically sensitive area to the north in about 48 hours, assuming that there was no emergency response mitigation. So the conclusion from this was this pipeline segment or facility would be identified as a could affect segment because we did identify that a resource could be affected. We could provide just minimum times. We could provide footprints. We could provide any number of data. Another example in the inshore environment was looking at a release from an example pipeline here. And again, we were looking at how oil would progress in this nearshore environment. And here we're going from a magenta color and oil reaching these locations in less than an hour up to the first HCA impacted here, another populated area within about 8.6 hours. But again, this footprint was cropped using GIS tools to essentially identify, here's the footprint at hour 8.6 when that first receptor was hit. The footprint would very likely be much larger if we looked at the entire 30-day example. Additional HCA results were provided in Wrapups. We provide very short reports, very concise, that can be delivered to PHMSA, and this data can be imported into the POD system. But we're, again, providing minimum time footprints as GIS shapefiles of the full 30-day unmitigated simulations. We're providing the same footprint, but for probability, again, as a GIS shapefile for the full 30-day unmitigated simulation. And those results can then be used by the operator to crop and to play around with to help guide other decision-making within the company. The technical reports were short, less than 15 pages. A lot of that is figures, but it's provided for backup and auditing purpose. It includes a brief introduction, modeling approach, and then the scenario development, modeling assumptions, results write-up, and then the conclusion, which honestly is about one sentence. It's whether or not this pipeline or facility is a could-affect segment. The operators we're working with are actually quite excited about using these tools, mainly because these results can be used to help guide many other things. They've been used for emergency response training, exercises and drills, oil spill response plans, environmental assessments, and otherwise aligning with a consistent approach within the company. Spill modeling is not new to this industry. It's been used for 40 years or more. And to have this kind of an approach developed in the offshore environment, and to understand that we're going to do an HCA assessment as well as a couple other things with the same modeling results, actually saves time and money at the end of the day. So what I've done is I've walked you through a little bit of that traditional on-land versus our new offshore HCA approach, mainly because of the changing winds and currents and tides in the offshore environment. The approach still holds in the traditional on-land assessment for those on-land facilities. It's got singular paths. It mainly applies because the land surface elevation isn't changing very much throughout the year. So that works very well for that application. But when we start to put our eye towards the offshore, as PHMSA had in the last year or so, and when we start looking at releases from pipelines, we do need to consider a little bit more comprehensive solutions like this approach, where we're considering the dynamic environment, providing a range of results based on the different environmental forcing, and the integration into different plans.